Hey everyone, we're going to start today by picking up with where we left off last time. And so if you remember last class, we discussed the concept of word vectors, and we saw the word tvec model as well as glove, which is an alternative popular framework. We talked a little bit about how to evaluate word vectors and how to interpret what they are doing. And so if you recall, we talked, oh, sorry, my slides seem to be, all right. And so just to kind of recap what we discussed about interpreting word vectors, they were, designed to perform this language modeling task, essentially to predict a word based on the surrounding context or predict the context based on the word. As we talked about, you can construct them both those ways, and it's going to lead to kind of a similar set of representations. And yet that's not typically a task that we want to perform, but the amazing thing about these vectors is that they seem to do a very good job of representing other meaningful properties about language. Like we saw the example how you could take king, subtract man, add woman, and that got you very close to king, queen. And we saw lots of analogies tasks like that. So that's just one example. And a takeaway from this, and also from all the other examples we've seen in the course and examples we'll continue to see, is that neural networks can learn better ways to represent data automatically than what we can engineer by hand. And this is important because if we're able to represent our data in a meaningful way, we can do all sorts of downstream tasks on it. And so this is a general kind of application of transfer learning. You train word vectors by having them predict the context based on a word, and then you could use those word vectors to do downstream sentiment analysis or other things like parts of speech tagging, parsing, etc. that we'll talk about more in a little bit. So, oftentimes we do this by starting with a model that's been initialized with pre-trained embeddings, and then we can fine-tune it on our task. But another powerful insight that we'll try to leverage kind of a little bit more as we move on in the course, because it's got kind of a lot of attention lately, is that another thing that you can do is try to embed two very different types of data into the same representation. And so very quickly at the end of last class, we saw a very simple to understand example about this, which was embedding words from English and Mandarin into the same word space, which is a paper from an older paper, actually from 2013, right after the word tvec paper came out. And it has pretty incredible results, because obviously like the words that you force to be close together because they are close translations are going to be close together, but it did a good job of putting words close together that the model didn't force them to do that. We didn't know in training that they are essentially translations of each other, but in this space the embedding like learned the shapes of these languages, and it seems to suggest that these languages, like as different as English and Mandarin are, they have these sort of similar shapes. And so when we force a limited subset of words that are close translations to be close together, it forces words that we don't know ex ante are close translations to also be close together. And importantly, nothing about this says that we can only embed data of the same type into a single representation. And so, a concept that's gotten kind of a lot more attention lately is, what if you tried to embed text and images into the same space? So take the example of, in training, you train the model so that when you show it a dog, it outputs the word vector or some other embedding representation of dog. And same thing when you input a cat. And then let's say you didn't train the model it didn't see a horse in training, But if you put in an image of a horse and it gave you out, you know, an embedding that's close to the word embedding for horse in that space, that would be an incredibly powerful model. Because like with an image classifier, you can't do that. Like you have to be exposed to all the classes in training. And so there's been a lot of interest in kind of zero-shot image classification with this sort of model that we'll talk about if we have time. And it also, I think, has a lot of promise for the future of OCR, because that in some sense is what you want to do. You want to take in an image and output a word, even if it wasn't exposed to that in training. Okay. So that was just a recap of what we had quickly gone over at the end of last class. And I want to talk a little bit about like potential sort of things to be aware about with word vectors. And this kind of goes for NLP more generally, but since kind of word vectors are a bit older, we've seen kind of more work done on that. And in particular, I want to talk about how word embeddings can reflect biases in the corpus. And so, you know, for us as social scientists, like we're not trying to design, you know, some sort of commercial product, and this may actually be what we want to study. And so, you know, it's not necessarily something that should prevent us from using NLP. I mean, maybe it's the point of why we want to use NLP, but there's been some kind of pretty remarkable work about the, you know, the biases that come out from word embeddings. And so this is an example of a paper that was looking at different types of occupations, and you can look, you know, going back to the idea that we talked about kind of last class about how, you know, STEAM is like very unlikely to be associated with solid and likely to be associated with gas, whereas ice is much more likely to be associated with solid than with gas, right? For obvious reasons based on the physical properties of those objects. But you could do something similar for like gender or for ethnic groups. And so this is a paper that was looking at gender biases in word embeddings. And so if you look at the occupations that are most likely to appear most likely to appear near she, like to have kind of she in the context, relative, you know, to having he in the context. And so these are occupations where when that word comes up, there's really likely to be a she nearby and not very likely to be a he nearby. You know, the number one on the list is homemaker, perhaps not surprisingly, nurse, receptionist, librarian, socialite, you know, hairdresser, nanny, housekeeper, where you have some like interesting things there for he, a skipper, philosopher, captain, broadcaster. They also did analogies tasks. And so you would say like, she is to sewing as he is to carpentry. She is to nurse as he is to surgeon. And you guys, you kind of like get the point. She is lovely. He is brilliant. And then they also did some kind of, those are the stereotype ones. They also did some kind of gender appropriate ones, right? Like she is to sister as he is to brother, where we would expect that. This is another example. And so this actually comes from image captioning. But if you guys like will remember when we went back to the visualization, when we talked about visualization in CNNs, we could see kind of like, you know, which part of, you know, the image would light up based on certain activations. And so the intuition is kind of similar here. So in image captioning, you put in an image and it outputs a caption. In a way, it's kind of similar to the OCR model because it's essentially taking a CNN features extractor and then using an RNN to write the caption. And you can see kind of which cells of the features map are most heavily weighted to write that caption, which is a pretty cool example, not just for bias, but kind of for general understanding how image captioning is working. So you can see in the far left column, it says a man sitting at a desk with a laptop computer. And if you look at the word embedding for man, what lights up and the dark red is the computer. And so it's inferring that there is a man there because it associates, you know, in the training data, men tend to be the ones that appear near computers. And so that's just wrong. Whereas this is an example of, you know, it's from their model of this paper that's cited here, which tries to kind of de-bias these things. You know, it gets that picture right. It says a woman sitting in front of her laptop computer, and you can tell that the part of the image that's lit up is actually kind of the correct part of the image that would allow you to identify that that's a woman. They also give an example of kind of right for the wrong reason. So a man holding a tennis racket, and again, when you look at the embedding man, the part of the image that plays heavily into that is actually the tennis racket, not the man. Whereas their model that tries to de-bias things, it's actually lighting up the man. And there's lots of other examples like this, like, you know, one of the most challenging thing to get right in ImageNet was detecting whether something was like a certain breed of wolf versus a dog, because wolves and dogs like happen to look very similar. And then kind of when models started to do better on this task, it turned out that it was because, you know, wolves tend to be like in the countryside, and dogs are more likely to be in an area around people. And that's kind of what was lighting up to get it right, like not the actual kind of animal itself. And that may be like a feature or a bug, kind of depending on what you want to do and depending on, you know, whether that bias is potentially like harmful, or it's just like an effective way to say that, you know, this is a picture of a dog. Okay. One of, I think, the best papers on bias and word embeddings is a PNAS paper by a group at Stanford called Word Embeddings, Quantify 100 Years of Gender and Ethnic Stereotypes. And so the general idea in this paper is that they take several different corpuses. And so they take Google News to get a modern corpus. I think that's mostly kind of post 2012 or so news content. And then they take, you know, an older data set that people use a lot in NLP that has like literature and that kind of stuff to look at things going back in time. And then they look at how the ethnic and gender biases of word embeddings shift or don't shift over time. And so here they're looking at today, like biases and talking about occupation. And so you can look at the female occupational share in the census. And so like women are like in the census, like very likely to be things like dancers or secretaries or librarians or nurses. But then you can look at the bias and the word embedding. So again, this is doing a very similar task to what we saw before. If you look at the word nurse, how likely is it that she is in the context relative to like the ratio that he is in the context? And you can see like, even though like, you know, women are likely to be nurses, like that's still kind of, there's an even greater exaggeration of that in the news media. And so the news media is very kind of unlikely to report on male nurses, and they're even more likely to report on, you know, female nurses than they are in the population. You see the opposite of that in the bottom half of the graph. So the news media is very unlikely to talk about women being engineers to an even greater extent than kind of like their underrepresentation in the like actual population in that field, or same with like carpenters, mechanics. And so this is kind of a cool visualization of this bias and word embeddings. And by using the census, they have kind of some measure of the ground truth. Then they want to look at this historically. They don't have news data historically, but they're looking at something called the Corpus of Historical American English and Google Books by decade, which is mostly like, you know, a corpus of books that have been digitized that a lot of the people in the digital humanities use for NLP. And they're again looking at biases and occupations and how they shift over time. And I think actually, like, you know, I don't, depending on what screen you guys are using, it may be very hard to read the numbers. But sort of what they're doing in this graph is the biases are shifting over time, and they look how correlated like the 1950s biases are with the 1940s biases, and then they do that for 1960 with 1950. And they find the correlation gets kind of modestly weaker at the start of the women's movement, right? So obviously this is kind of like a very kind of rough descriptive exercise, but it seems sort of consistent with what you would expect. There seems to be kind of a more rapid change or breakdown in the biases of these word embeddings for female occupation. And again, the whole time they're like kind of controlling for actual occupation shares in the census, because that can be shifting as well. What they're interested in is this kind of additional bias in the corpus. So here they're looking for the top adjective that's associated with woman. And so they're using 3 decades, 1910, 1950, and 1990, again, from this corpus of historical American English database, which basically has like kind of draws on a lot of kind of books from Google Books. And I mean, I don't know enough about this corpus to know the extent to which there could be kind of biases or anything in how it's selected. But this is kind of like interesting to look at. And I think that kind of the words here you see are not necessarily very surprising. Like in 1910, women are charming, placid, delicate, mellow. And you see some of the same things you actually see a lot of the same words in 1950, although there start to be maybe some things like tasteless there. And then you see things shift a little bit in 1990. So there's like less this emphasis on women maybe being fragile, but kind of the stereotypes you might expect: maternal, caring, emotional. I guess soft kind of goes along with some of the prior ones. They also look at race, and so they take the most common Asian last names and versus the most common white last names. And so think about this as a little bit analogous to what the paper that Sindel and Marianne have, like on, you know, traditionally white versus black names and the response to resumes. This is kind of something a little similar, but they're just looking at what adjectives appear and are predicted as most likely to appear, like in the contexts of traditionally Asian last names versus as compared to traditionally white last names. And so you can see this is like pretty bad, irresponsible, barbaric, aggressive, monstrous, hateful, cruel, greedy, bizarre. Things don't really look that much better in 1950. Unprincipled, venomous, disobedient, predatory, boisterous, unstable, pompous, outrageous. It's all like unquestionably like really negative. Maybe it's, you know, things get a little bit better in 1990. There's still kind of negative stereotypes, by and large: passive, haughty, complacent, forceful. But I think you can see here kind of some shifts in stereotypes that have happened across time. And this probably, like, I should say, understates things, because if you're bothering to refer to somebody by like their name, like you're already like giving them a certain amount of dignity. And I'm sure that in this earlier period that it was also pretty common to just use like racial slurs to refer to groups of people. So I'm sure that that would kind of make it look even worse. And again, they kind of look at these correlations across time. So how much are things shifting? And they point to certain events that they argue could lead to shifts and biases. I mean, again, it's a bit loose, but one could actually imagine like potentially doing a very similar exercise, but with some specific policy that you might have causal identification on, or with a corpus that gives you variation kind of across space and time. And so I think that the method is like really powerful, even if the correlations are a little bit loose. Okay, so that's biases in embeddings. Basically, I mean, your model's going to learn what you train it on. And I should say this is like a point that goes kind of well beyond, inherent kind of human biases that are in our data. It's also like, let's say you just want to digitize a table. Okay, well, you don't have to worry about the sorts of issues that we just saw. But if you're careless in labeling and you label something wrong and you miss a cell of the table, your model's going to learn how to detect it wrong. And so actually like high quality labels are imperative. And so, I mean, the bottom line is that your model is going to learn what it's trained on. And so if you train it on a bunch of racist text, it's going to learn that, and maybe that's like the point if your goal is to study kind of racism in these contexts, but like it's good to be aware of if you train it on poorly constructed labels or even kind of modestly careless labels, it's gonna again like learn to do things wrong because all it knows is kind of what you've trained it on. Okay, so I'm gonna wrap up word vectors just by saying one last thing, which is the problem with the technical problem with word vectors is word sense ambiguity. Most words have multiple meanings, and this is very, very prevalent with common words. And so the more common the word is, like the more likely it is to have multiple meanings. So like you could say, I took my money to the bank, I walked along the river bank. There's just tons of examples like that. And actually the most common words that you are likely to see in your text are the most likely to have that problem. And also the older the word is, it becomes much more likely that it has multiple meanings. And so we're gonna see a way to address this. We're getting there, but I just want to flag that is, if you're thinking about it, this would probably jump into your mind as being a major issue with word embeddings, as we've seen them, and indeed that's true. And so, in the word to vec framework, each word has like a representation. And that's true even if the word has a lot of different meanings, and it's just going to be kind of some average of those. And so we want a way to deal with that, and indeed models that deal with that problem are going to outperform word to vec. But word to vec is still, I'd say like, word to vec is kind of the NLP equivalent of AlexNet that we saw earlier, and that it jump-started the whole kind of deep learning revolution in NLP. So it's super important to know about, and you'll see it referred to a lot, even if people are less likely to use it today. Okay, so now I want to move on to talking about language models. So we've already talked about this a little bit, because to talk about OCR, we had to talk about RNNs and lstm, which have been kind of workhorse language models, and we talked about word to vec, but I want to talk about language models a little bit more systematically. And then I'm going to talk about a few other things, dependency parsing, named entity recognition. And these are topics that were like really some of the dominant topics in computational linguistics. And so you could take an entire course on them, and it gets kind of technical, but I just want to explain what these terms mean, like why you might need to use them, and like what package you should use if you need to use them. And I'm not going to go into the technical details. And then I'll say a little bit about labeling for NLP, because when we get to kind of doing downstream tasks, and so as you've seen, like the word to vec, the language modeling itself is unsupervised, but we're going to be talking about, later in the course, we're going to be talking about things like doing sentiment analysis, For example, in which case, like you have to tell, there's some zero-shot approaches, or a few-shot approaches, but in general, like you have to tell the model what a sentiment is. So you're going to need to label. And I just want to say a quick kind of fits into this lecture. So this lecture is a bit of like a potpourri of like different topics that, weren't enough to have kind of an entire lecture on their own, but are things that you should know about, like if you're using NLP. Okay, so I want to start by talking about language modeling, which we've already seen a little bit, but what I wanted to do today is give a little bit more of a historical perspective on how people traditionally did language modeling, and I'll also give just a brief review of the RNN and lstm stuff that we saw earlier. And then next week, we're going to spend the week talking about the transformer, which is sort of the modern language modeling architecture that people tend to use. But I think you'll understand better why that's so powerful if you first know how people did this historically, and what the problems are with that. And the other reason that you should know about that is like sometimes in economics papers, people still use like, methods from NLP that are 10 or 15 years old. And you guys shouldn't do that. You're going to know that there's much more powerful methods out there. Not that there could never be a case to use the traditional methods, but kind of usually you wouldn't want to do that. But you may still see people using them and saying like, oh, I'm doing, this, high-tech NLP stuff, and you should understand kind of where that fits in. And so the goal of language modeling, as we've already talked about it at various points, is you want to understand, is a sentence probable? And language modeling aims to answer this question with the following framework, where you have, the probability that a sentence will appear, and that's just the product of the probability of the next word given the context. And so let's say that we have, to make that concrete, we have a sentence like, the girl went to school. And intuitively, kind of, we know that that's a probable sentence. If you have the girl, there's a high probability that went comes next. The girl went to, there's a high probability that school comes next. And you just kind of multiply those probabilities. How much of the context you take into account is going to vary with the model, but that's the general idea. How probable is it kind of that the next word in the sentence appears? So if instead you had something like school to the girl went, well, we know that that sounds wrong. And, how would you quantify it? School to, it's not that likely that to comes after school. School to the girl, you can to the girl went, those kind of successive, as you're moving over predicting the next word based on the context. If you've trained this on Wikipedia, you're going to know that that sentence is not likely to happen. And you haven't seen that sentence before. That's in kind of your test set, but based on your training data, sentences of that type don't appear. And so we want a way to capture this. And so, well, why would we use this? And so if you wanted to use a language model directly, you'd use it for things like scoring sentences. So, you're using Google Docs or Grammarly, and it tells you that there's a grammar error, well, like, one way you could think about a grammar check is this sentence probable? Autocomplete is another obvious thing. For us, as economists, it's usually a means to some other end. Although there might be reasons with your OCR why you need to like spell check or grammar check it, and language models are a powerful basis for that. So you might use the language model directly, but oftentimes, even if you think, well, with the data I have, it's already this clean modern text, I don't care about this, this task of predicting the next word. Well, actually you do, for the reason that we saw with word vectors, that in order to predict the next word, you need to create a representation of the data that's going to be very powerful for downstream tasks. And so if you look at modern NLP methods, where did they come from? Well, Google is a big player, like the transformer architecture that we'll see. was created by people at Google, like Facebook created a follow-up to that. And so in short, like Google has many reasons for directly using language modeling. So this is an example of something I put into Google, and when it auto-completes that for you, that is precisely language modeling. NLP is, and based on everything that people put into Google search, it's going to predict what comes next. So NLP is fake, NLP is a cult, NLP is pseudoscience. Some people think NLP is fun. It's the sort of thing where you don't necessarily like want to know. I remember that one time I was at like a dinner with some other faculty, and they started talking about somebody had put one of our colleagues in, and then like, you know, the top autocomplete was like his name, wife. And then people are like, oh, people must be really interested. Like maybe they see him as being really, you know, eligible. And then it turned out you put in anyone's name, and that's like pretty much like the top thing that comes up, just probably because people are just like nosy, I guess. But anyways, like Google takes everything that, you know, everybody ever puts into Google and like trains an autocomplete model. And if you go and do this in Google Scholar, it's going to look really different because people using Google Scholar are using it for different things than people using Google. Okay, so for us, maybe we don't particularly care, but actually, like, we're going to see that, you know, and as you kind of saw a little bit in the paper on word vector biases, which is just also like, you know, I think the paper is intended to be a cautionary tale of building your like, you know, search recommendation system on top of this. But for us as social scientists, it's actually a fascinating way to study biases in society and the things that influence them. And like, there's so many applications like this. So you should see this as like an amazing and unintended gift from Google to social science research, that they created this commercial product that is actually going to be incredibly useful for a lot of your research. And so that's just like pretty amazing, and something that is worth, you know, paying the startup costs so that you can take advantage of this. Because I think, you know, yeah, without Google, it's not clear that like kind of our kind of modern architecture for NLP would exist. Okay, but let's step back. And suppose that we're kind of like starting from scratch, and we want to say, how would we go about calculating the probability that a sentence is likely? Well, one way, and the way that people kind of initially thought about, is that, you know, all the way back in the 1960s, like people were interested in doing this, and they tried to do it using human engineered rules. You'll recall all the way back, I think, to the second class, we saw some examples of rules, and we've seen a few examples where they can be useful, lots of examples where they can be problematic. So let's think a little bit about kind of what would happen if you were trying to use rules to do NLP tasks. Okay, so all you want to do here is to, you know, you want to engineer your own language model. So you want to say, is this sentence likely to appear or unlikely to appear? And if you're trying to do that based on a rule, like here's an example, Jane went to the store. Okay, that's a very standard sentence. But then there's kind of variants of that. Store to Jane went the. You know, it has all the same words, but the grammar is messed up. Or Jane went store. I mean, it has all the same information, but that's not how we say that. Jane go to the store. Like, you know, you need to create a grammar. And as anybody who's kind of learned English as a second language, or most languages as a second language knows, like there's many exceptions to grammar. You need to code the morphology and exceptions to it. The store went to Jane. That's grammatically correct, but stores tend not to go to people. We think of them usually as some sort of fixed location. So we'd say that sentence is not probable. The food truck went to Jane. Well, maybe that's okay. A food truck is a kind of store, but it can move. And so we'd also need to hand engineer rules for like semantic meaning and exceptions. And you can see that this is just going to be an impossible task. There's just, at least for like a general model, there's just no way you can write rules that encode all the complexity of the English language. And of course, we don't just care about English. So here's, generally speaking, kind of a similar set of sentences, but they're in Japanese, and now you need a totally different set of, rules about the grammar to encode this, and so you're gonna have to start all over again, right? And so you're really like, this is just not going to, get you very far. But I mean, people tried to do stuff like this, just when the field was starting out. Okay, so instead, what people did before there was deep learning was to use count-based models. And this was kind of the engine of computational linguistics and the pre-deep learning era, and you'll still see these used sometimes. And so the idea is to predict the next word using the frequencies of word sequences. So you're just counting up frequencies from your training data. So let's say that you want to compute the probability of the teacher read. You count up how many times the teacher read appears in your corpus, and you divide it by how many times the teacher appears. And kind of same thing with anything. Like, I went to the store. You count up how many times that appears, and you divide it by how many times I went to the appears. And then you're going to calculate the log likelihood of all sentences in your corpus by essentially, just summing over this probability that we just saw. And then, so the intuition here is, let's say that you have a corpus of test data. So these are data that you did not see when the counts were computed on the training data. And you're going to use the model, those probabilities that you computed already in training, to compute the probability of each sentence and sum up over all sentences in the corpus. If the model is extensible to your test data, then your likelihood should be higher. Whereas if you've trained your model on different text and it hasn't been, really exposed to things like what it's seen in your test data, then it's going to kind of give a lower probability. Or if your test data, let's say the model's doing a good job, but your test data is full of grammar errors or whatever, that should give a lower likelihood. And so that's the basic idea. You can also normalize by the number of words in the corpus. And so this is often known as an n-gram model, which is a term that you kind of may have seen if you've looked much at the NLP literature in social science. And so an n-gram is a sequence of inconsecutive words. And so like a unigram is just one word. So if the sentence is, this class covers NLP, this is a unigram, class is a unigram, so on and so forth. A bigram is two consecutive words. So this class covers NLP. A trigram is three consecutive words. This class covers NLP. A fourgram, this class covers NLP. And you use counts of different n-grams to predict the next word. Okay, so these models are very, simple to understand. We can explain them in a couple of slides, and if you understand what a count is, you can understand what the models are doing. But there's some problems with these models. And so it's going to treat all words as IID. That's going to inherently be a problem because any language is full of many synonyms. Importantly, it can't handle long distance dependencies. So take an example. For ballet lessons, she needed to bring her new shoes. For tennis lessons, she needed to bring her new ball. In order to predict that the next word is shoes, you need to remember that ballet occurred in the sentence, but that was a long time ago. For reasons we'll see, n-grams cannot encode that type of long-range dependency. To predict ball, you need to remember that tennis appeared, and n-gram cannot do that. And these long-range dependencies are like essentially like the norm of human language. And so why can't it do that? Well, there's a couple of reasons. The first reason is sparsity. So let's say this class covers blank, or this class covers mask. We put a mask token there. And we want to correctly predict that NLP appears there. This class covers NLP. But if this class covers NLP never occurred in the training data, then we have a problem. We can't predict that. I mean, there's always going to be unseen things, but even worse, suppose this class covers never appeared in the training data. Well, you can't divide by 0. So now you kind of really have a problem. Your model is undefined. The way that people kind of did try to deal with this is to use a technique called back off, where if this class covers doesn't appear, they would just look and see if class covers appear. If class covers doesn't appear in the training data, you just look if covers appears. Importantly, this sparsity problem becomes more severe as n increases, right? So the longer the length of dependency that you take into account, the less likely you were exposed, the model was exposed to that specific n-gram in training. So in practice, these models just don't work if n is bigger than 5, and it's more common to use kind of like a 3-gram. You start running into these major sparsity problems, and so you just cannot get these longer dependencies, like in the sentence in that middle bullet point there, and that's a problem. The other reason why you can't have larger n-grams is that the size of the model grows exponentially in n, and so you just can't save all those n-grams and compute the model. And so there's a Stanford linguistics course that gives the following example of text generated by a 3-gram. It says, today the price of gold per ton, while production of shoe lasts in shoe industry, the bank intervened just after it considered and rejected an IMF demand to rebuild depleted European stocks. September 30th, end primary, and so you get the point that this is just garbage. Like n-grams cannot really like accurately generate text. And why is that? Well, it's because we need those long range dependencies. That's what makes like a sentence, let alone a paragraph or an entire page coherent. But if we increase n, it will worsen sparsity and exponentially increase model size. So we just can't do that with an n-gram. And so, the alternative would be to use featureized models. We calculate features from the context, we learn the weights used to calculate the features, and we compute probabilities from those features. And so this is an example of, just to compare deep learning generated text from a model called GPT-2 that's like a couple of years old actually now, maybe a few years old. And so it gets like a prompt, a train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. And you can see it generates this entire kind of coherent, story around it. The incident occurred on the downtown train line, which runs from Covington and Ashland stations, and an email to Ohio news outlets. And this kind of goes on, and it all like sounds like, kind of coherent. And so, the differences in other downstream tasks, so maybe we don't care about generating text based on a prompt, but differences on other downstream tasks like sentiment analysis or retrieval that you guys probably do care about are going to be similarly striking. And so if you want to use text data in a meaningful way in your research, there's just no excuse for not understanding and being able to apply modern deep learning methods, which are going to just lead to like massive improvements. Like when it comes to NLP, what may have been fine for a paper 5 years ago is not necessarily something that you would use today. The field moves very fast. Okay. So that's count-based models. Are there any questions? Okay. So I also want to say a bit about kind of how we would use this sort of approach for downstream tasks. So I'm going to talk about bag of words, which takes all words in a sentence and makes predictions just based on those words, kind of regardless of the syntax. And so, for example, in doing sentiment analysis, you may have a score for the probability each word in a sentence is associated with each sentiment to be classified. A bag of words just adds up those probabilities. So to see that in a picture, suppose you're doing sentiment classification on like Yelp reviews. and somebody writes, I hate this movie, like so I guess it would be on movie reviews. So you want to classify that as very negative, right? I hate this movie. And so let's say you have like 5 categories for the 5, nodes showing. So like, really dislike, neutral, like, really like. And with bag of words, for each word independently is associated with something. So like well, that's used in every imaginable context. It doesn't tell you about sentiment. Maybe that's neutral. Hate, that's going to give you a very strong, strongly dislike. This, again, is not really telling you anything. Maybe movies, also neutral. You can add those up. So you may have some bias. So let's say on Amazon, like it's most common for reviews to be 5-star. Then you would want to kind of bias your model towards the classifier saying that it's 5 stars. And so with bag of words, you just look up each of those words and you add up their vectors and you add the biases, and that gives you a score. And then you take a softmax, and that's how you do your sentiment analysis. And again, you're going to see this actually used in, especially like I think political science papers that are a bit older that used NLP, some economics papers. People use this a lot. But it's not hard to kind of see how this is problematic. So if you consider, and this is basically why, you'll go to like an economics talk that's using NLP, and people will say, well, we can't do sentiment analysis on this, but actually you can. You just need kind of the more modern methods. Maybe like, 5 years ago, it would have been a lot harder, but things are really changing. So just consider the following, like, I hate this class, I don't love this class, I don't hate this class, there's nothing I don't love about this class. And so you can see how obviously, if you're just treating each word independently and you have just a vector associated with don't and hate and love, you can see how this is not going to work. Like, you cannot capture this sort of structure. There is nothing I don't love. You can't capture that with bag of words. You need something that takes combinations of words, combinations of features. You just can't do that with just adding up a vector for each word. And so, well, how are we going to take some complicated? So essentially, we want to take, we look up each word, and then we want some complicated function to extract the combination of features. And then we use that to do the softmax and get our probabilities. Well, how do we approximate a complicated function? I mean, again, if you learn just one thing from this course, it's that you use a neural network to approximate a complicated function, right? So this is kind of essentially what bag of words does. You have a lookup for each word, but then it takes that into, it has this complicated function, and you're going to do dramatically better because now like different words, different features that you look up are allowed to interact. Okay, any questions about bag of words? Okay, so I'm just going to quickly review RNNs and LSTM, just so we already went over this, but just to make sure you guys have it in your mind. And so remember that an RNN is a deep learning model that allows outputs or inputs to be variable length sequences, which we talked about in the context of OCR because our output is a variable length sequence of words, but obviously that's often true in NLP tasks as well. And so essentially, an RNN is fed an input vector at every time step and also maintains an internal state, and it can modify that state as a function of what it receives at each time step. And so this is kind of what is hopefully allowing us to model those kind of long-range dependencies. We have a history at each period, which is some kind of complicated function that we're going to estimate with deep learning of the previous history and our input at each step. And then we can produce an output YT at each step based on that history. And importantly, we're going to apply the same weight function at every step. And that's what allows us to use an RNN with arbitrary length sequences, regardless of the sequence length. We use the same function at every step. And so a plain vanilla RNN, you might have a set of weights for your history and a set of weights for your input, and you combine those, put it through a TANH, and that updates your history. and then your output, so maybe the words you're predicting for OCR, or whatever you're using the RNN for, is itself going to be matrix multiplication between another set of learned weights and the history. And you're going to do that at each time step. Now, as we talked about, we wouldn't ever actually use this RNN formulation in practice because of the vanishing gradient problem. And so if you'll remember, we talked about, we've talked multiple times about how gradients flow through networks. When you're doing backprop, you apply the chain rule. And so you get the gradient by taking the local gradient and multiplying it by the upstream gradient. And how the gradient distributes is going to depend on the operation that occurs at that node. And so we tend to like addition because that just distributes gradients. So here you have a node that's performing an operation. The green numbers are the output you get on the forward pass, and the red numbers are the gradient from the backwards pass. And so if you add, well, you just distribute out the gradient because the derivative of x plus y with respect to x is 1, ditto with respect to y, and so the gradient just distributes. Where you get in trouble in RNNs is with a multiplication gate because the derivative of ax with respect to x is a. And in an RNN, remember the whole point is that you use the same weight metrics at every time step. Because that's what allows you to have an arbitrary linear sequence. But you can show that if you're multiplying by the same weight matrix over and over and over again, if the largest singular value is greater than 1, the gradient explodes, and if it's less than 1, it will vanish. And so that is effectively going to mean you can't learn long-range dependencies, because when you get back to the earlier part of your network, you're multiplying that W over and over again, and your gradient is going to tend to go to 0. And we just saw that we have to have long-run dependencies if we want to do a good job of modeling language, because they're essentially human language. And so in practice, we saw that people would often use an lstm, which is a model that dates back to 1997. And I'm not going to, just for the quick review, I'm not going to go into the details again. But the basic idea is that in addition to the history, you have the cell state that's just internal to the model. And you compute the cell state at each time step by multiplying it times this forget gate, which tells you how much you should remember the previous state, and then adding it with an input gate, which says whether or not to write to the cell at this time step, times how much to write to the cell. And then this kind of cell value is just internal to the model. And you also have a history, which is what determines the output from each stage of the model. And the history is just equal to the output gate, which is telling you times the cell state. So the output gate tells you how much to write out the cell state. And this might seem like a little bit of an idiosyncratic architecture, but as we saw, the key reason why this works is that cell state is giving you uninterrupted gradient flow through the network. So it's going to help you deal with the vanishing gradient problem. The only reason you're going to have a vanishing gradient is if you always forget everything, which you can just avoid by initializing your model so that you don't forget everything. And as we talked about, this is very similar to ResNet, where we similarly had these add gates, or what they call skip connections, that allow for unimpeded gradient flow. And it also relates to this idea of highway networks. And so I'd say this idea, you can't really have deep learning without this idea. Some combination of these 3 papers is kind of transformed what deep learning can do. And LSTM kind of had this insight decades before it was sort of rediscovered in other, and now again in the deep learning context. And so if, it's this idea that in order to train a really deep network, which is what you need to model these kind of long-run dependencies, you have to have kind of some way to make sure gradients flow through the network so you can update the earlier phases of the network. So this is just a generally important insight into making backprop work. Okay, I know that was a bit of a quick review since we'd seen it before, but are there any questions? Okay, I'm going to talk now about dependency parsing, and as I said, like you could oftentimes like spend like a few lectures on this in an NLP course. This kind of dominated computational linguistics and the, you know, in the pre-deep learning days when the only people doing NLP were like by and large linguists. And I don't want to get into all the technical details because it would take us way too much time. And it's kind of tedious unless you're interested in linguistics. And so the idea behind dependency parsing is that it maps dependency relationships between words in a sentence. The reason I do want to talk about this is that I think it can actually oftentimes be quite useful. And so, for example, well, I'll go into an example in a minute, but basically I think that there are reasons why this can be useful to our research. So I'm going to tell you kind of what it is and what package to go look at. And so why it might be useful, I mean, this is just one example I've come across, and I'm sure you guys can think of other ones. So it's not uncommon that there's information that could have actually been written as a database, but it was written in a pretty formulaic way as text. And so one example that we've come across of that is historical biographies. And they tend to be written in this way, like person A studied in department, in university, in place, during the years, under the tutelage of person B. And you'd like to turn this into a database because you want to map the relations between people or institutions or places in this biographical data. And to do that, you essentially need to do dependency parsing and named entity recognition. So you need to know what the named entities are, but you also need to know the dependencies between them. You need to be able to extract that person A studied under person B, right, which is a dependency in the sentence. And I suspect that it's not uncommon for useful information to be presented in this format. So I suspect you guys may find applications of this in your research. Okay, so dependency parsing is hard. We don't really think about it necessarily, but there are many, many ambiguities in human language. So I'm gonna pull a few examples from a lecture that was given by a leading scholar in dependency parsing, Christopher Manning of Stanford, and they're in English, but this is much more broadly true across languages. So here's something called prepositional phrase attachment ambiguity. San Jose cop kill man with knife. And you guys can see how that could be ambiguous. Did the man have a knife or did they kill him with the knife? That's a dependency ambiguity. Scientists count whales from space. Does from space refer to the whales or to the scientists, right? Like, and these ambiguities actually multiply with the length of the sentence. And it's not uncommon to have like, you know, 5 or more ambiguous prepositional phrases that are in succession, you know. So if you spend much time talking to little kids, you'll like see that some of like the adorable things that they say are based on like trying to figure out what prepositional phrases refer to. Coordination scope ambiguity. This is an article about Trump, doctor, no heart cognitive issues. And so is he saying no heart issues and no cognitive issues, or is he saying he has no heart and has cognitive issues, right? It's ambiguous. Verb phrase attachment ambiguity. Mutilated body washes up on Rio Beach to be used for Olympic beach volleyball. And again, like, you know, there's an ambiguity there. We can understand that fine, but how are you going to teach the computer to understand that? Like, and in this talk, there were actually a lot of other examples of ambiguity, but some of them I thought, like, I'm not sure that that's appropriate to bring up that example of ambiguity in class. It was probably more entertaining than my lecture is, though. And so this is like a feature, not a bug of human languages. Like, so if you take programming languages, you're not allowed to have this kind of ambiguity, and programming languages are much less efficient to communicate with than human languages. Like the fact that we don't have to resolve all these ambiguities, that you just assume that you're talking to somebody who has the cognitive capacity to understand what you mean, even though the language doesn't pin that down, allows our communications to be very efficient. But it makes things really difficult because we need a computer that will resolve these ambiguities. And so how dependencies are denoted in the literature, sometimes you see them with arrows in sentences. So in this sentence, I prefer the morning flight through Denver. The route is prefer, and I is dependent on that. Flight is dependent on that. And this comes from a textbook treatment of this, which if you guys are interested, you may want to check out. It's the textbooks online for free. Or even more often, you see them written as these dependency trees. And so I is dependent on prefer, and flight is dependent of prefer. The morning, those are modifiers of flight to Denver or through Denver. Denver refers to flight and through refers to Denver. And so the idea of dependency parsing is you have kind of all these potential dependency trees, and you want to choose the correct one. Oftentimes along with this, you'll see people denote parts of speech. Obviously, if you're using different languages, there may be some differences there. And you can also do parts of speech tagging with this, which could come in useful sometimes as well for parsing. So labeled data for dependency parsing are called tree banks. And there's something called universal dependencies that has labeled data on dependencies for over 100 languages and is constantly being updated. So as I said, this was the big problem kind of in computational linguistics. And so there's actually quite a lot of labeled data to work with. Going back to our biography example, that was an example where it was kind of a very narrow use case that tended to say things in this kind of formulaic way, but that might not have looked like the data that's in this universal dependencies bank. In which case, you're going to want to label some data and fine tune on your example. But fortunately, something like biographies, it's pretty formulaic, so you probably don't need a huge amount of labeled data for fine tuning. But that raises the question of, well, how am I going to estimate dependencies and how am I going to fine tune? And fortunately, there's a really fantastic and well-developed and easy-to-use package for dependency parsing that's called Spacey. So you can go and download it. You'll see an option to use a fast or an accurate version. And so the accurate version uses a transformer architecture, which we're going to talk about next week to embed input. And they say it leads on average 30% more accurate results, which is a pretty big deal for our application. So you probably want to get the accurate Spacey. And so the general idea is kind of, they embed the information using one of these transformer-based models that we'll talk about, and then you can do things on top of that, like you can do dependency parsing, or you can do named entity recognition. So it has dozens of languages, pre-trained pipelines for common tasks, like dependency parsing in 17 languages. And so you can kind of already see the pipeline they go through, which is really helpful. Multitask learning with pre-trained transformer-based models. So that's useful. Maybe you need to do dependency parsing and you want to tag parts of speech and you want to recognize named entities. You can do that in a multitask framework where you're trying to optimize the embeddings for all three of those tasks. It has components for dependency parsing, but also named entity recognition, part of speech tagging, entity linking, text classification, and other common tasks. Importantly, it supports custom models in PyTorch. And so again, maybe, kind of the pre-trained models aren't going to be the perfect fit for your application, but they make it and they're very kind of careful about, I think, how they set up their configurations and trying to just make it easy to use, relatively speaking, for you to fine tune your own model. There's visualization for things like syntax and named entity recognition. So I keep talking about named entity recognition. What do I mean? Well, you have different entities in a sentence and you try to recognize their class. And so these are kind of the classes that are built into the pre-trained spacing model. There's a person, nationalities or religious or political groups, buildings, airports, companies, countries, cities, geographic places, you can see that it kind of goes on. And this is going to be very useful maybe for your applications, because let's say you're trying to extract the biographical data and it's always of the form so-and-so went to university X in place Y at date Z. Where if you can tag the university as a named entity, place as a named entity, and date, which is also a type of named entity, then you've kind of extracted potentially like what you want. And so again, like this is really useful, and Spacey makes it relatively like straightforward, you know, because if you had to code this from scratch, first of all, you have to understand what it's doing, and there's like, you know, a ton of architecture and stuff that goes into this, but they make it pretty straightforward to either use off the shelf or to fine tune to your context. Which brings me to a final point, which is that if you want to use Spacey for fine tuning, you're going to need some labeled data. Fortunately, the makers of Spacey also have a labeling tool called Prodigy that's designed to make it easy to label for NLP. And this is a tool, even if you're not using, you're doing something that Spacey doesn't do. You may still want to use Prodigy because it's really like the main tool out there that's been designed for NLP labeling. You know, it's a paid tool, but you can get like a trial version to try it out. And it just makes things much more efficient than if you're sitting there trying to do something in like Excel or whatever else you might use. So this is an example of labeling for named entity recognition. So you can use the tool to say, I want to, you know, I'm looking for 4 types of entities: a person, an organization, a product, and a location. And then you put in, you know, they're giving examples of labeling headlines. And so you can just click on the pretty people in that, you know, just click and you can label the locations, etc. So it's like super easy to create labels. And they're also going to store it in like the format that you need for training their models, which is always like a bit tricky. Like, you know, if you're doing object detection, you need COCO format, you need certain formats for doing named entity recognition, and it will take care of that conversion for you. Labeling for topic modeling. Okay, so let's say you have 4 topics and you're going to label headlines by their topic. Again, that's something you can do in Prodigy. So in short, again, if you're doing NLP and you need to kind of fine tune, this may be a tool that you should check out. Okay, are there any questions about any of this? I know it was like a quick overview, but I'd say like the bottom line is like kind of understand that these are tasks that you can do where you're tagging dependencies or parts of speech or entities. And if you find yourself needing to do that, like go check out Spacey. Okay, thank you guys.